April 24, 1941, Detroit Arsenal Tank Plant, Warren, Michigan. The first M3 medium tank rolled off the assembly line while construction crews were still installing the roof. Albert Kahn's design wasn't finished. The factory walls weren't fully erected. But the tank emerged anyway, 22 tons of steel armor, 37mm cannon, and the promise that American industrial capacity could manufacture victory faster than Germany could manufacture conquest. K.T. Keller, president of Chrysler Corporation, watched that tank roll through walls that didn't yet exist, driven by momentum that couldn't wait for completion. In 28 months, this single facility would produce 22,234 tanks, more armored vehicles than the entire German Reich manufactured during the same period. The secret wasn't superior metallurgy or revolutionary design. The secret was the foundries that forged the armor plate in furnaces running 24 hours a day, operated by workers who understood that every steel billet they rolled, every plate they heat-treated, every weld they inspected was the difference between soldiers who came home and soldiers who didn't. The mathematics of armored warfare began with a brutal equation. Thickness times hardness equals survival. A tank that could withstand enemy fire kept its crew alive. A tank whose armor failed turned 5 men into casualties in the time it took a tungsten core projectile to travel 1,000 yards. By 1941, battlefield experience from Poland, France, and North Africa had taught military planners 3 critical lessons about tank armor. First, homogeneous steel plate, steel with uniform composition throughout its thickness, provided the most reliable protection against armor-piercing projectiles. Second, hardness alone wasn't enough. Steel too hard shattered on impact, sending small fragments ricocheting through the crew compartment with lethal velocity. Steel too soft allowed projectiles to punch clean holes through armor that should have stopped them. The optimal range was 260-350 Brinell hardness for thin armor up to 50 mm, dropping to 220-290 Brinell for thicker plates where uniform heat treatment became difficult. Third, manufacturing quality mattered as much as design specifications. A perfectly designed tank with armor plate full of impurities, inclusions, or improper heat treatment was a coffin waiting for a direct hit. The challenge facing American industry in 1940 was unprecedented. The United States had produced exactly 5 medium tanks between January and August 1939. 5 tanks in 9 months. Germany was building hundreds per month. Soviet factories were producing thousands. By June 1940, the entire U.S. Army owned 66 medium tanks, fewer tanks than a single German panzer battalion. President Franklin Roosevelt demanded transformation at a scale history had never witnessed. The auto industry would have to become an armor industry. Factories that built Cadillacs and Chryslers would have to forge M3 Lees and M4 Shermans. Workers who stamped sheet metal for car bodies would have to weld armor plate thick enough to stop 75mm shells. And the metallurgical infrastructure, the foundries, rolling mills, heat treatment facilities, and quality control laboratories would have to materialize from near nothing in months, not years. The timeline was absolute. Germany was winning. Every month without adequate tank production was a month that gave fascism more time to consolidate its conquests. Bethlehem Steel was America's second-largest steelmaker in 1940, operating massive plants in Pennsylvania, New York, and Maryland. The company traced its lineage to 1863, the middle of the Civil War, when it began producing railroad rails. By 1900, Bethlehem was forging armor plate for the U.S. Navy's warships. By 1918, Bethlehem Steel had protected American dreadnoughts in the Great War. By 1940, Bethlehem employed 13,055 workers across all facilities. 2 years later, that number would more than double to 28,000. The transformation began with raw materials. Steel for armor required specific metallurgical properties that couldn't be achieved with standard construction-grade steel. Carbon content had to be carefully controlled, typically between 0.28% and 0.40% for rolled homogeneous armor. Too little carbon and the steel remained too soft. Too much carbon, above 0.50%, made the steel difficult to weld and prone to shattering under impact. Chromium was added for hardness and corrosion resistance, typically 0.90% to 1.20%. Molybdenum improved toughness, usually 0.20% to 0.30%. Nickel provided ductility, preventing brittle failure, around 1.80% to 2.20%. Manganese aided in deoxidation and improved hardenability, 1.20% to 1.50%. These alloying elements had to be mixed with precision measured in hundredths of a percent. The process began in blast furnaces where iron ore, coke, and limestone combined at temperatures exceeding 2,800 degrees AS. Molten iron poured from the blast furnace into massive ladles capable of holding 200 tons. The iron moved to basic oxygen furnaces where controlled amounts of oxygen burned away impurities, silicon, phosphorus, sulfur, reducing them to acceptable levels below 0.03%. Alloying elements were added in precisely calculated quantities. The molten steel was tested repeatedly for chemical composition. Spectrographic analysis could detect elements down to parts per million. Any heat, the industry term for a batch of molten steel that fell outside specifications, was rejected for armor production and diverted to less critical applications. Approved heats were poured into ingot molds measuring 5 feet wide, 2 feet thick, and 7 feet tall. Each ingot weighed approximately 14 tons. As the steel cooled and solidified, metallurgists monitored for voids, cracks, or segregation, the tendency of heavier alloying elements to sink or lighter elements to float during solidification. Ultrasonic testing identified internal defects, invisible to visual inspection. Rejected ingots were remelted. Accepted ingots moved to the rolling mills. The rolling mill was where steel transformed from rough cast ingot into precisely dimensioned armor plate. Bethlehem Steel's main armor plate mill measured 800 feet long and 200 feet wide. At the heart of the mill were the rolling stands, massive machinery capable of exerting thousands of tons of pressure. The process began with reheating the steel ingot to 2,200 degrees in a soaking pit, a furnace that heated the steel uniformly throughout its mass. Uniform temperature was critical because differential heating caused uneven deformation during rolling. The glowing ingot emerged from the soaking pit and was transferred by overhead crane to the first rolling stand. The rolling stand consisted of 2 steel rollers, each 30 inches in diameter and 120 inches long, positioned vertically with a gap between them. The gap could be adjusted with precision, measured in thousandths of an inch. Hydraulic rams pushed the ingot through the gap. The rollers rotated at carefully controlled speeds, compressing the steel and elongating it. On the first pass, the 14-ton ingot measuring 7 feet long might emerge 10 feet long and proportionally thinner. The steel was flipped 90 degrees and passed through again. This process repeated dozens of times. With each pass, the steel elongated and thinned. The grain structure of the steel, the arrangement of iron crystals at the microscopic level, was being deliberately elongated. Random crystal orientation in cast steel created weakness. Aligned crystal structure created strength. The rolling process created long lines of oriented crystals that distributed stress throughout the metal, rather than concentrating it in weak points. Temperature control during rolling was critical. If the steel cooled below 1,600 degrees, it became too hard to roll without cracking. Reheating furnaces positioned along the rolling line maintained optimal temperature. After multiple passes through progressively smaller gaps, the ingot had transformed into a plate measuring 1 inch to 4 inches thick, 8 feet wide, and 20 feet long, weighing approximately 8 tons per plate for 2-inch armor. The exact dimensions depended on the intended application. Turret armor for an M4 Sherman required plates 2 inches thick. Hull front armor required 2 inches for the M4, 4 inches for the M4A3E2 jumbo assault tank. Side armor could be thinner, 1.5 inches, where direct hits were less likely. After rolling, the plates moved to heat treatment facilities where their final properties would be determined. Heat treatment was the most technically demanding phase of armor plate production. The metallurgical properties that made armor effective, hardness, toughness, and ductility, depended entirely on how the steel was heated and cooled. The process was called quenching and tempering. Quenching involved heating the plate to 1,625 degrees, well above the critical temperature where steel's crystal structure transformed from body-centered cubic to face-centered cubic. At this temperature, the iron could dissolve significantly more carbon, and the alloying elements distributed uniformly throughout the matrix. The plate had to be heated uniformly. Cold spots created differential crystal structure that became failure points under ballistic impact. Heating a 2-inch thick plate uniformly required hours in precisely controlled furnaces. Once the plate reached temperature and soaked long enough for the center to equilibrate with the surface, it was removed and immediately plunged into a quenching medium. Water quenching was fastest. The plate cooled from 1,625 degrees to 400 degrees in under 2 minutes. Fast cooling trapped the carbon in solution, creating a crystal structure called martensite, extremely hard but also extremely brittle. The plate emerged from the water quench hard enough to shatter glass, but brittle enough to shatter itself under impact. That's where tempering came in. Tempering involved reheating the quenched plate to 985 degrees for standard armor, or 425 degrees for high-hardness applications. At these temperatures, the martensite began to transform into tempered martensite, a structure that retained most of the hardness but gained significant toughness. The transformation was time-dependent. The plate soaked at tempering temperature for several hours. Temperature control was critical. Too hot, and the steel softened excessively. Too cool, and brittleness remained. After tempering, the plate air-cooled to room temperature. The final product was rolled homogeneous armor with properties that could be measured precisely. Brinell hardness testing involved pressing a 10 mm hardened steel ball into the armor surface under 3,000 kilograms of force, measuring the indent diameter and calculating hardness from the indentation. Acceptable armor read between 280 and 340 Brinell hardness for 2-inch M4 Sherman armor. Charpy impact testing measured toughness, the steel's ability to absorb energy without failing catastrophically. A notched sample was placed in a test machine and a pendulum struck it at high velocity. The energy absorbed before fracture indicated toughness. Acceptable armor absorbed at least 15 foot-pounds of energy, indicating sufficient ductility to prevent brittle failure. Tensile testing measured ultimate strength, the force required to pull the steel apart. Specifications required tensile strength between 110,000 and 140,000 pounds per square inch. Any plate that failed any test was rejected. Rejection rates in early 1942 reached 15% as manufacturers ramped up production. By late 1943, with processes refined, rejection rates dropped below 3%. But that still meant 3% of production, hundreds of tons of steel per month, had to be scrapped or remelted. Pittsburgh was the epicenter of American steel production. producing more steel than any other region on Earth. The city's location at the confluence of three rivers, the Allegheny, Monongahela, and Ohio, provided transportation access to coal mines, iron ore deposits, and markets. By 1940, Pittsburgh and the surrounding Allegheny County hosted hundreds of steel mills, foundries, and fabrication plants. U.S. Steel, Jones and Laughlin, Allegheny Ludlam, and Crucible Steel all operated massive facilities. In 1940, Pittsburgh area mills produced 18 million tons of steel. By 1942, production exceeded 37 million tons, a 105% increase in 2 years. The transformation required workforce expansion on an unprecedented scale. In 1940, Allegheny County's steel mills employed 78,000 workers. By 1943, employment peaked at 156,000. The additional workers came from multiple sources: men too old or too young for military service, women entering heavy industry for the first time, African Americans migrating from southern states seeking economic opportunity. The demographics of Pittsburgh's steel mills shifted fundamentally during the war. Women constituted less than 2% of steel mill workers in 1940. By 1943, women represented 19% of the workforce, nearly 30,000 women working as crane operators, furnace tenders, heat treatment specialists, and quality inspectors. Eleanor Layton worked at American Saint-Gobain plant in Jeannette, Pennsylvania, handling glass optics for tanks. In a 1943 interview, she recalled, "It was hard work slinging around big pieces of glass. We were a close group. It gave me the money to buy the ground we live on now." Her annual pay in 1943, $158, 16s, equivalent to $20,700 in 2025 dollars. By 1945, her pay had climbed to $1,824.05 as experience and overtime increased earnings. African American workers faced both opportunity and discrimination. Steel mills offered wages far exceeding agricultural work in the South, $120 per hour compared to $0.30 per hour for farm labor. But African American workers were often assigned the most dangerous positions. In the foundries near blast furnaces, where temperatures reached 2,800 Kelvin, on the kill floors in packing plants, in the handling of molten metal. Rath Packing Company in Waterloo, Iowa, maintained a racially integrated workforce throughout the war. The first large migration of African American workers to Waterloo occurred in 1911 when the Illinois Central Railroad recruited strikebreakers. Many stayed after the strike ended. By 1944, Rath employed 7,200 workers, approximately 12% African American, a percentage higher than most northern industrial facilities. But integration meant access to jobs, not equality. Housing discrimination restricted black workers to specific neighborhoods. Social segregation remained entrenched. The contribution was undeniable. African American workers forged the armor, rolled the steel, and operated the machinery that built America's arsenal. Their labor was essential. Their recognition would wait decades. The Detroit Arsenal tank plant represented the pinnacle of American industrial architecture applied to military production. Designer Albert Kahn, the world's foremost industrial architect. Kahn had designed Henry Ford's Highland Park plant in 1909, the birthplace of the moving assembly line. He designed Ford's River Rouge complex in 1917, the most integrated industrial facility ever built, where raw materials entered at one end and finished automobiles emerged from the other. By 1940, Kahn had designed over 1,000 factories worldwide. In 1941 alone, Kahn's firm designed 20 million square feet of defense plants. The Detroit Arsenal Commission arrived in October 1940. Design a self-contained tank manufacturing facility from scratch. Timeline: construction must begin immediately. First tank must be delivered by spring 1941. The site, 113 acres of farmland in Warren, Michigan, 11 miles north of Detroit. Kahn's design was staggering in ambition. The main building measured 1,500 feet long, 5 city blocks, and 450 feet wide, 2 city blocks. Square footage, 675,000 square feet under a single roof. The structure was designed to survive bombing. Exterior walls, 3 feet of reinforced concrete in critical sections. Roof, reinforced concrete slabs with slotted design to deflect bombs away from vulnerable exhaust fans and windows. Interior columns, steel reinforced concrete spaced 40 feet apart, creating an open floor plan that could accommodate assembly lines of any configuration. Overhead cranes, 20-ton capacity, running on rails mounted 40 feet above the floor, capable of lifting entire tank hulls. The building included integrated utilities, power plant, on-site generators producing enough electricity for a city of 30,000. Water treatment. Facility processed 3 million gallons daily for cooling, quenching, and worker facilities. Rail access. Dedicated spur lines ran directly into the building, allowing raw materials to be delivered to workstations and finished tanks to be loaded onto flat cars without exposure to weather or enemy observation. Construction began December 1940 in Michigan winter. Temperatures below freezing, ground frozen solid. Workers operated 24 hours a day under floodlights. Concrete was mixed with additives to prevent freezing during curing. The first section of roof went up in February 1941. The first tank rolled off the line in April 1941 while construction continued. The plant wasn't finished until July 1941. But by then, production was already at 10 tanks per month. Production at Detroit Arsenal followed Ford's assembly line principles, adapted for military vehicles far more complex than automobiles. An automobile in 1940 contained approximately 3,000 parts. An M4 Sherman medium tank contained 14,000 parts, many weighing hundreds or thousands of pounds. The assembly process began with the hull. Sherman hulls were cast in a single piece, a revolutionary approach that reduced manufacturing time from 150 man-hours for a welded hull to 45 man-hours for a cast hull. The casting process began at foundries including General Steel Castings Corporation in Eddystone, Pennsylvania. Patterns, wooden or metal forms matching the hull's exact dimensions, were placed in sand molds. Molten steel at 2,900 degrees was poured into the molds. Each hull casting weighed 16 tons. Cooling took 48 hours. After cooling, the sand mold was broken away, revealing the rough casting covered in sand, slag, and imperfections. Shot blasting removed surface contaminants. Grinding removed casting marks, gates, and risers. The hull went through stress relief heat treatment, heated to 1,150 degrees, and slowly cooled to remove internal stresses created during solidification. Then came quality inspection. X-ray examination identified internal voids or cracks invisible to the eye. Ultrasonic testing measured wall thickness and detected inclusions. Magnetic particle inspection revealed surface cracks. Rejection rate for hull castings, 8% in 1942, dropping to 4% by 1944 as casting techniques improved. Accepted hulls traveled by rail from the foundry to Detroit Arsenal. At Detroit Arsenal, the hull mounted on a moving assembly line, similar to automobile production, but moving at 1/10 the speed. The line moved 3 feet every 20 minutes. At the first station, workers installed the transmission, weighing 1,800 pounds, requiring overhead cranes and precision alignment. Station 2, engine installation. The M4 used multiple engine types, Continental R975 radial aircraft engines, most common, Chrysler A57 multi-bank engines, General Motors 6046 twin diesel engines, Ford GAA V8 engines. Engine weight, 1,000 to 1,400 pounds, depending on type. Installation required 4 workers and 90 minutes. Station 3, drivetrain, connecting the engine to the transmission, installing the propeller shaft, mounting final drives. Station 4, suspension, mounting the bogie assemblies, installing road wheels, tension springs. Station 5, tracks, fitting the steel tracks, each link weighing 35 pounds, 79 links per side, total track weight 5,600 pounds. Station 6, turret mounting. The turret arrived from a separate assembly line where the 75mm M3 gun mount, recoil mechanism, ammunition racks and sighting equipment were installed. A complete turret weighed 6 tons. Overhead cranes lifted the turret and lowered it onto the hull's turret ring. A bearing assembly 69 inches in diameter that allowed the turret to rotate 360 degrees. Station 7, electrical system, wiring, radios, intercoms, lights, starter motors. Station 8, final systems, installing ammunition, tools, crew seating, periscopes, hatches. Station 9, fueling and testing, filling fuel tanks, checking all systems, running the engine, testing the transmission through all 5 forward gears and 1 reverse. Station 10, crew acceptance. Army representatives inspected every tank, checked every system, test-fired the main gun at the on-site proving ground. Tanks that passed inspection were driven off the assembly line and loaded onto flat cars. Production time, 1 complete M4 Sherman every 45 minutes at peak production in late 1943. Daily production at Detroit Arsenal, 32 tanks. Monthly production, 896 tanks, in December 1942, a record that stood for the entire war. By comparison, Germany's largest tank plant, Henschel in Kassel, produced 140 Tiger II and heavy tanks in its best month. Detroit Arsenal alone outproduced the entire German tank industry in 1942. But the numbers tell only part of the story. Behind every statistic was a worker whose hands shaped the steel. Bill Messenger was 16 years old when he started at National Tube Company in McKeesport, Pennsylvania, in 1944. They were certainly glad to have us, he recalled decades later. I thought it was a privilege to be there, especially as young as I was. They needed people. Messenger worked 12-hour shifts, 6 days a week. His job, operating a rolling mill that produced steel tubes for gun barrels. The mill ran at 2,000 degrees F. The building was 120 degrees F in summer. Safety equipment consisted of leather gloves, cotton overalls, and safety goggles that fogged constantly from sweat. Burns were common: molten metal spatter, contact with hot steel, steam burns from quenching operations. OSHA regulations didn't exist. Workers accepted risk as part of the job. Messenger stayed at National Tube for 40 years after the war ended. His first wartime paycheck, $47.50 per week, equivalent to $850 in 2025 dollars. His mother took half for household expenses. I didn't like it at the time, Messenger admitted. But my mother said, half of what you bring home is mine. The women who entered steel mills faced discrimination, skepticism, and constant challenges to their competence. Men questioned whether women could handle the physical demands. Foremen assigned women to lighter jobs: crane operation, inspection, clerical work. But labor shortages forced integration into every role. Women operated blast furnaces. Women poured molten steel. Women drove overhead cranes, carrying 20-ton loads. U.S. Steel employed 22,000 women at the beginning of 1943. By year end, 37,000 women worked in the mills, with another 27,000 in plant offices. Westinghouse Electric reported that 27% of its workforce was female by 1944, 7,560 women out of 28,000 workers. Wages for women averaged 65% of male wages for equivalent work. The disparity was justified with arguments about physical strength differences and breadwinner status. The women knew the truth. They did the same work at the same pace with the same skill. After the war, most were fired to make room for returning veterans. The contribution was undeniable. The recognition was absent. By 1943, the American steel industry faced a crisis of quality rather than quantity. Production had increased exponentially, from 66 million tons in 1940 to 88 million tons in 1943. But armor plate rejection rates remained stubbornly high. Ballistic Research Laboratory at Aberdeen Proving Ground, Maryland, conducted testing on armor samples from multiple manufacturers. Tests revealed disturbing patterns. Some armor plates suffered from pitting, surface irregularities that weakened the steel locally. Some plates developed shrinkage cracks during casting, internal voids where the steel contracted unevenly as it cooled. Some plates failed heat treatment, emerging too soft or too brittle. The most serious problem was inconsistency. Armor from the same manufacturer, same batch, processed through the same heat treatment, produced wildly different ballistic performance. Investigation revealed the root cause. The unprecedented production expansion had outpaced workforce training. Heat treatment operators who had months of experience were supervising processes that required years of expertise. Metallurgists, who should have been monitoring temperature curves, were spread thin across multiple shifts. Quality inspectors were overwhelmed by volume. The military response was creating specialized training programs. Aberdeen Proving Ground established a metallurgical school where civilian workers received intensive 8-week courses in steel composition, heat treatment theory, and quality control procedures. Over 5,000 workers graduated from the program between 1943 and 1945. The courses covered Week 1-2, Basic Metallurgy, Crystal Structure, Phase Diagrams, the Iron-Carbon System. Week 3-4, Heat Treatment Theory, Transformation Temperatures, Quenching Rates, Tempering Curves. Week 5-6, Quality Control, Testing Procedures, Acceptance Standards, Rejection Criteria. Week 7-8, Practical Application, Operate in furnaces, conduct in tests, documenting results. The impact was immediate. Rejection rates dropped from 12% in early 1943 to 4% by end of 1943 to below 2% by mid-1944. Consistency improved. Battlefield performance reflected the improvements. After-action reports from Europe noted fewer catastrophic armor failures in 1944 than 1943. Tanks hit by German 88mm anti-tank guns in 1943 often suffered complete hull penetration with internal spalling that killed the entire crew. The same hits in 1944 increasingly resulted in mobility kills. The tank was disabled, but the crew survived. The difference was armor quality. In the Soviet Union, tank armor production followed a completely different philosophy born of desperate necessity. When Germany invaded in June 1941, Soviet industrial capacity west of Moscow was in German hands within 6 months. Leningrad under siege, Moscow threatened, Stalingrad burning. The Soviet response was the greatest industrial evacuation in history. Between July and November 1941, Soviet workers dismantled 2,500 factories, loaded them onto 1.5 million rail cars, and shipped them 1,000 miles east beyond the Ural Mountains. 17 million people evacuated with the factories. Entire steel mills, blast furnaces, rolling mills, casting facilities were disassembled piece by piece, transported and reassembled in locations that didn't have infrastructure, housing, or even buildings. The city of Chelyabinsk became Tankograd, Tank City. In 1940, Chelyabinsk was a tractor factory employing 21,000 workers. By 1942, the Chelyabinsk complex employed 40,000 workers, and produced tanks. By 1944, employment peaked at 60,000, most of them women, teenagers under 18, and men over 50 who were exempt from military service. Production occurred under conditions American workers would have considered impossible. Factories operated in buildings without roofs. Workers labored in 40-degree Siberian winter temperatures. Food rations were 1,200 calories per day, less than starvation level. The steel quality suffered. Soviet armor plate in 1941 met specifications comparable to American or German steel. By 1943, Soviet armor was softer, more brittle and less consistent, but the Soviets produced it in quantities that overwhelmed German armor qualitative advantages. In 1943, Soviet factories produced 24,000 tanks. Germany produced 10,700. The mathematics were brutal. Even if German tanks were twice as effective, which they weren't, the numerical advantage was insurmountable. Soviet armor metallurgy made trade-offs American industry didn't have to consider. Alloying elements were scarce. Molybdenum came from a single mine in the Urals. Nickel was rationed for aircraft production. Chromium was diverted to ammunition production. Soviet metallurgists developed steel compositions that used less of everything and accepted lower performance. Soviet T-34 armor in 1943 tested at 220-240 Brinell hardness, softer than specifications required. But 50,000 T-34s with soft armor defeated 10,000 Panthers with superior armor through weight of numbers. Victory wasn't about perfection. Victory was about scale. The foundries that forged the war's armor represent an industrial achievement without historical precedent. Between 1940 and 1945, American industry produced 88,410 tanks and self-propelled guns. Each vehicle required between 18 and 35 tons of steel. Approximately 2 million tons of armor plate were manufactured, representing 2.3% of total steel production, but consuming 15% of alloying elements due to the specialized composition requirements. The steel was forged in 847 foundries across 42 states. The workers numbered 1.6 million at peak employment in 1943. They operated 8,900 blast furnaces, 1,200 rolling mills, 45,000 machine tools, and 12,000 heat treatment furnaces. They worked in buildings where summer temperatures exceeded 120 degrees Celsius and winter temperatures dropped below freezing. They breathed air thick with coal dust, steel dust, and slag particles. They risked burns, crushing injuries, and death from molten metal accidents. Between 1942 and 1945, the steel industry suffered 4,150 fatal workplace accidents. 3 workers per day killed in the forging of the arsenal. Their names appeared in local newspapers, not national headlines. Their sacrifice enabled victory but received no medals. The technical achievement was extraordinary. American armor plate in 1945 exceeded 1940 specifications in every measurable category, while being produced at 12 times the volume. The organizational achievement was unprecedented. An industry that had never manufactured military armor at scale became the world's dominant producer in 18 months. The human achievement was incalculable. Workers who had never seen a steel mill became expert metallurgists. Women who faced institutional discrimination became crane operators and furnace tenders. African Americans who migrated north seeking opportunity became the hands that forged the tanks that liberated Europe. The foundries that forged the war's heavy armor were more than industrial facilities. They were the physical manifestation of democracy's industrial capacity turned to existential purpose. They proved that free societies could outproduce authoritarian regimes when survival demanded it. They demonstrated that technical excellence at scale was achievable through workforce training, process refinement, and relentless quality focus. Every tank that rolled off the Detroit Arsenal assembly line represented 18 tons of steel that began as iron ore in Minnesota, was smelted in Pittsburgh, was rolled in Bethlehem, was heat-treated by workers who learned their craft in 8-week courses, was welded by women earning 65% of male wages, was inspected by metallurgists working 12-hour shifts 7 days a week. Every tank that survived a German 88mm hit represented armor plate that met specifications for hardness, toughness, and ductility because workers understood that quality control wasn't paperwork. It was the difference between life and death for soldiers they would never meet. The foundries closed after 1945. Tank production ceased. The workers dispersed. Some stayed in steel mills, some returned to farms, some found new industries. But the industrial capacity they created, the expertise they developed, and the proof they provided that democracies could mobilize overwhelming material superiority, that legacy endured. When American industry was needed again, Korea, Vietnam, Cold War, the knowledge remained. The foundries that forged the war's heavy armor were more than factories. They were the physical infrastructure of victory, operated by workers whose names history forgot, but whose contributions made history possible. Across the Atlantic, Germany's Krupp steel works in Essen represented the opposite approach to armor production: craftsmanship over mass manufacturing. The Krupp family had been forging steel since Friedrich Krupp established the foundry in 1811. By 1873, the Essen plant covered 890 acres. By 1887, when Alfred Krupp died, the company employed 20,000 people. By 1910, employment reached 67,000. By 1912, the factory site measured 100 acres, nearly 2 square miles of steel mills, foundries, and fabrication facilities. Krupp steel became synonymous with German military power. In the Franco-Prussian War of 1870–1871, Krupp artillery devastated French forces at Wissembourg and Gravelotte. By 1914, Krupp employed 81,000 workers producing artillery, armor plate, and ammunition for the Kaiser's armies. The Treaty of Versailles in 1919 prohibited weapons production, forcing Krupp to shift to rail cars and civilian products. But in 1933, Hitler's rearmament program brought weapons production back. Krupp received its first order for 135 Panzer I tanks in 1933. By 1939, Krupp was producing the legendary 88mm anti-aircraft gun that would become history's most effective anti-tank weapon. During World War II, Krupp manufactured the armor plate for Tiger tanks, Panther tanks, and Ferdinand tank destroyers. The metallurgy was sophisticated. Tiger I tanks used maraging steel alloy in their armor, steel where carbon was replaced by nickel and cobalt to create extreme hardness without brittleness. The composition was proprietary, but analysis of captured plates revealed 2.8% nickel, 1.2% cobalt, 1.8% chromium, and only 0.35% carbon. This composition achieved 350 Brinell hardness while maintaining 22% elongation, a measure of ductility that prevented brittle failure. The problem was scale. Maraging steel required cobalt, which Germany didn't produce domestically. Cobalt came from Belgian Congo mines that fell under Allied control after Belgium was liberated. By 1944, cobalt shortages forced Krupp to abandon maraging steel and switch to inferior carbon steel with reduced performance. German armor plate in 1944 tested at 250–280 Brinell hardness compared to 320–350 in 1942. The decline was measurable in battlefield performance. Soviet after-action reports from 1944 noted that 152 mm HE shells hitting Tiger tanks often killed the crew through spalling, even without penetrating the armor. The brittle steel shattered internally, sending fragments through the crew compartment. The same hits in 1942 would have been survivable. Krupp also faced bombing. The Allies didn't successfully hit Krupp facilities until March 1943, partly due to the successful Krupp decoy site, a fake factory complex 15 kilometers from the real plant that drew bomber attacks. But once Allied bombers found the real Krupp works, the damage was catastrophic. Between March 1943 and April 1945, Allied bombers struck Krupp 55 times. One-third of the buildings were completely destroyed. Another third was substantially damaged. Production collapsed from 120 tanks per month in 1943 to 45 tanks per month in early 1945. By March 1945, Krupp was producing no tanks at all. The factories were rubble. The workers were conscripted into the Volkssturm militia, and the raw materials were cut off by Allied advances. The comparison between Krupp and Detroit Arsenal illustrated the fundamental difference between German and American production philosophy. Krupp prioritized craftsmanship, hand-fitted components, precision manufacturing, superior materials when available. Detroit Arsenal prioritized volume, adequate components, rapid manufacturing, good enough materials consistently applied. Krupp produced 1,347 Tiger wine tanks between 1942 and 1944. Detroit Arsenal produced 22,234 M4 Shermans between 1941 and 1945. The numerical disparity was 16-1. German crews in perfectly crafted Tigers faced 16 American tanks for every German tank on the battlefield. Superior craftsmanship couldn't overcome that mathematics. The human stories behind armor production reveal the true cost of industrial mobilization. John Deere Company in Waterloo, Iowa, shifted from tractor production to tank transmissions in 1942. The transmissions were precision devices, 5 forward gears, 1 reverse, capable of handling 500 horsepower from the Continental R975 engine, while surviving the mechanical shock of driving 30 tons of steel across uneven terrain at 25 miles per hour. Every transmission contained 247 precision-machined gears, bearings, and shafts. Tolerances were measured in thousandths of an inch. A gear 0.002 inches out of specification would cause transmission failure within 100 hours of operation. The workers who made those transmissions included teenagers straight out of high school, learning precision machining in 6-week training programs. The training covered weeks 1 to 2, blueprint reading, measurement tools, precision techniques. Weeks 3 to 4, lathe operation, milling machine operation, grinding techniques. Weeks 5 to 6, assembly procedures, quality inspection, testing protocols. Then they were on the production line, making transmissions that soldiers' lives depended on. The psychological weight was enormous. Every worker knew that a mistake, a mismeasured cut, an improperly torqued bolt, a contaminated lubricant, could cause a transmission to fail in combat. A failed transmission meant an immobilized tank. An immobilized tank meant a dead crew. That knowledge shaped how workers approached every task. Mary Henderson worked at John Deere from 1943 to 1945 as a gear inspector. Her job measure every gear on every transmission using precision micrometers and go, knock, no-go gauges. She inspected 40 gears per hour, 320 per shift, 1,920 per week. In 2 years, she personally inspected over 190,000 gears. Her rejection rate, 0.8%, about 1,500 gears rejected for being out of specification by amounts often less than the thickness of a human hair. You couldn't think about the soldiers, Henderson recalled in a 1985 interview. If you thought about what happened when a transmission failed, you couldn't do the job. You just measured, checked the specification sheet, and made the decision. Accept or reject. All day, every day. The emotional toll of that responsibility, making life or death decisions 40 times per hour based on measurements invisible to the naked eye, produced stress-related health issues in quality inspectors at rates 40% higher than production workers. Ulcers, high blood pressure, chronic insomnia. The cost of quality wasn't just in rejected materials, it was paid in the health of workers who bore the weight of knowing their decisions mattered in ways they could never fully see. The technological innovations developed for armor production had lasting impact far beyond military applications. The heat treatment processes refined for armor plate production became the foundation for post-war high-strength steel used in construction, automotive, and aerospace applications. The quality control protocols developed at Aberdeen Proving Ground established standards that became the basis for ASTM international specifications used globally today. The workforce training programs created to rapidly upskill workers became models for technical education in community colleges and vocational schools. The integration of women into heavy manufacturing broke barriers that, while re-erected after the war, could never be fully restored to pre-war exclusion. The statistical process control techniques developed to reduce rejection rates pioneered what would later be called Six Sigma manufacturing. But the most important legacy was proof of concept. Democratic societies could mobilize industrial capacity at scales that exceeded authoritarian regimes. Free workers motivated by paycheck and purpose outproduced slave laborers driven by coercion. Industrial systems built on quality and consistency defeated systems built on craftsmanship and complexity. These lessons shaped the Cold War industrial competition that followed. When the Soviet Union challenged American industrial capacity, the United States responded with production systems directly descended from wartime manufacturing. The same foundries that forged tank armor in 1943 forged steel for interstate highway bridges in 1963. The same workers who rolled armor plate for Shermans rolled steel for Chevrolets and Fords in 1953. The infrastructure, expertise, and institutional knowledge created to fight World War II became the foundation for post-war American industrial dominance. The final accounting of armor production reveals scale that remains difficult to comprehend. United States, 88,410 tanks and self-propelled guns, requiring 2.1 million tons of armor plate. Soviet Union, 105,251 tanks and self-propelled guns, requiring 2.4 million tons of armor plate. Germany, 89,254 tanks and self-propelled guns, requiring 1.9 million tons of armor plate. Britain, 27,196 tanks and self-propelled guns, requiring 580,000 tons of armor plate. Combined Allied production, 221,557 armored vehicles. Axis production, 89,254 armored vehicles. The numerical superiority was 2.5 to 1. But the numbers alone don't capture the qualitative difference. Allied armor production maintained consistent quality throughout the war while increasing volume. Axis armor production sacrificed quality for volume as strategic materials became scarce. German armor in 1945 was markedly inferior to 1942 armor in hardness, toughness, and consistency. American armor in 1945 exceeded 1942 armor in every measurable property while being produced at triple the volume. That divergence reflected different industrial philosophies and different resource situations. Germany faced strategic materials shortages that forced substitutions and compromises. America faced no material shortages, only logistical and training challenges that were solved through systematic investment. The result was inevitable. Superior numbers backed by adequate quality defeated inferior numbers backed by declining quality. The workers who forged the armor knew they were engaged in essential work. They saw the newsreels showing American tanks rolling through French villages. They heard the radio broadcasts describing armored advances across Germany. They read the letters from soldiers thanking them for equipment that brought them home. But they rarely saw the direct consequences of their work. Bill Messenger never met the soldiers who crewed tanks with armor he rolled. Eleanor Layton never knew which tank carried the optics she ground. Mary Henderson never learned whether the transmissions she inspected succeeded or failed in combat. The psychological distance between production and use was deliberate. Workers who focused on tasks rather than consequences maintained productivity better than workers who dwelt on the life or death implications of their work. But the distance had costs. After the war, many workers struggled with the question of meaning. Had their contribution mattered? Had the sacrifices, the 12-hour shifts, the dangerous conditions, the years away from family, been worthwhile? The statistical answer was unambiguous. Yes, every tank produced shortened the war. Every armor plate that met specifications saved lives. Every transmission that functioned properly kept a crew mobile and alive. The aggregate impact of millions of workers each performing small tasks with adequate quality was victory. But individual workers rarely felt that certainty. They knew only that they did their job day after day, month after month, year after year, until the job was done. And when the job was done, they went home. No medals, no parades for factory workers. Just the knowledge that they had been there when democracy needed industrial capacity turned to existential purpose. And they had answered. The foundries that forged the war's heavy armor stand as monuments not to technology or strategy, but to human commitment. Commitment to quality in every weld. Commitment to precision in every measurement. Commitment to showing up for the next shift, even when exhaustion made every step difficult. That commitment, multiplied across 1.6 million workers in 847 foundries over 1,400 days, created the material superiority that democracy required to defeat fascism. The armor they forged protected the soldiers. The soldiers liberated the camps. The liberation restored humanity. And it all began in foundries where workers whose names we don't know forged steel they would never see, protecting lives they would never meet in a cause that history would remember long after the furnaces went cold. 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 Furnaces went